Welcome to video 1 of your next chapter, and our next chapter is going to focus on quadrilaterals. We're going to focus on all the different kinds of quadrilaterals, these special quadrilaterals, and we might occasionally talk about how some quadrilaterals are just quadrilaterals. They just have 4 sides. So today we're going to focus on classifying our quadrilaterals. What are all the different kinds of quadrilaterals? We will discuss this chapter. Now, on your papers, you have the following types of quadrilaterals. These are special quadrilaterals that have actual special names. We have kites, we have trapezoids, isosceles trapezoids, parallelograms, rhombuses, rectangles, squares. These are the main 7 special quadrilaterals that we will discuss. Now, there are some slight variations for the definitions that you might have originally kind of grown up knowing, and it's kind of changed a little bit, and it really depends on the textbook that you use. And we'll talk about why there's a difference between some textbooks and the definitions of our quadrilaterals. The main thing being would be kites, trapezoids, and parallelograms in general. If you look in your textbook, this isn't what it just says the definition of a kite is. There's another additional part that I kind of whited out and got rid of. So a kite, what we're going to go with is that it's a quadrilateral with 2 pairs of adjacent sides that are congruent. So notice these adjacent sides are congruent and these adjacent sides are congruent. So there's our 2 pairs of adjacent sides that are congruent to each other. Your textbook states that the opposite sides cannot be congruent, but we're not going to go with the textbook definition. We're going to go with this it's going to be more of an inclusive type of definition. A trapezoid, the way I had always known a trapezoid was that it had exactly 1 pair of parallel sides. But things have kind of changed, and again, we'll talk about why. But a trapezoid isn't just going to be exactly 1 pair of parallel sides. Its definition is going to be that it's at least 1 pair of parallel sides. And a parallelogram is a trapezoid with both pairs of opposite sides parallel. Before, a parallelogram and trapezoid were 2 completely separate things. They were not even related to each other. But now we are going to have this relationship between a parallelogram and a trapezoid. A parallelogram is a kind of more evolved, specific kind of trapezoid. So a trapezoid has at least 1 pair, which means it could have 1 pair or it could have 2 pair. So again, we could call a trapezoid this shape, but we could also call a trapezoid this. A parallelogram is a trapezoid. A rhombus is a parallelogram, and a parallelogram is a trapezoid. So technically a rhombus is a trapezoid with 4 congruent sides. A rectangle is a parallelogram or a trapezoid with 4 right angles. And a square is a parallelogram or a trapezoid with 4 congruent sides and 4 congruent angles. Now, what I make note here is these are just the definitions. There's plenty of other properties that are true about these shapes in terms of their sides, their angles, and we'll also focus on their diagonals. Okay, and again, the diagonal pieces will be the lengths that go from one angle to a non-adjacent vertex over to another. So there are some special things that happen with diagonals in terms of lengths and in terms of angles that we will explore this chapter. Now, as we mentioned, a parallelogram is a trapezoid, a rhombus is a parallelogram, which is a trapezoid, a rectangle is a parallelogram, which is a trapezoid, a square is a parallelogram, which is a trapezoid. So what do all 4 of these shapes have in common? Well, they're all parallelograms, but they're all technically trapezoids. Okay? Now, what do these 4 shapes have in common? We'll say that they are trapezoids and they're parallelograms. I mean, a parallelogram is a parallelogram, right? It's kind of the reflexive property there. So what should we technically see in all 4 pictures? Well, if all 4 of these shapes are technically parallelograms, which are trapezoids, we're going to focus on the parallelogram part here. Parallelograms have opposite sides that are parallel, which means a rhombus, which is a parallelogram, should also have opposite sides that are parallel. But you'll notice in the picture that that's not present. So really what you could do is you could draw in the parallel side markings. Make sure you put the appropriate number of parallel markings on the opposite sides here. Same thing is going to apply with a rectangle. You know, technically its opposite sides are parallel. So we could also show that. And the same thing goes for a square, that its opposite sides are technically parallel, but they're not marked that. Okay, it's kind of implied that if a square is a parallelogram, then technically we can take all the properties of a parallelogram, even its definitional pieces, that being the opposite sides are parallel, and it should also apply to this. But a square has more than just opposite sides that are parallel. It also has 4 congruent sides and 4 congruent angles, 4 right angles. So just keep in mind that if we see a shape like this, we know it's a rectangle, and technically its opposite sides are still parallel, even though the markings aren't there. They're implied there. Now, the father of geometry, really, the guy way back when, old Greek times, that really started making definitions of shapes is Euclid. And Euclid wrote a book called The Elements. And, it's kind of like the Bible of geometry, if you will, because it's kind of split up into different books and different definitions. And so this is what Euclid said about shapes. He said, of quadrilateral figures, a square is that which is both equilateral and right-angled. So equilateral meaning that it has all congruent sides, and right-angled meaning that it has right angles, and really that they're all congruent angles in there. An oblong, that which is right-angled but not equilateral. So really, Euclid's oblong is our rectangle. A rhombus, that which is equilateral but not right-angled. So that kind of applies still today. And a rhomboid, that which has its opposite sides and angles equal to one another, but is neither equilateral nor right-angled. So Euclid's rhomboid is really our parallelogram. So this is something that is some properties that will be true about a parallelogram. The opposite sides and angles will be equal to each other, but not all the sides are equal, and not all the angles are equal, therefore 90-degree angles. And let quadrilaterals other than these be called trapezia. Now, this is where the argument comes into play of, well, a trapezoid or a trapezia here, does that mean that it has one pair of parallel sides, or does it mean that it could have 2 pair of parallel sides? Where do kites fit into this? What about isosceles trapezoids? So Euclid really didn't have it all together, 2,000 plus years ago. There were still some holes. And so people along the years have come along and tried to finish some definitions because we've come up with kind of other shapes besides what Euclid knew about. So there's where you'll see some textbooks will say trapezoids have exactly 1 pair of parallel sides, and other textbooks will say that it's at least 1 pair. And we're going to go with more of the at least 1 pair, and I'll explain why once we kind of look at the family tree of quadrilaterals. All right, let's take a look at the quadrilateral family tree. It's the kind of weirdest family tree. You don't really want to be a part of this family because there's a lot of connections that you really wouldn't want to claim to your friends, like, well, hey, my dad and my uncle are the same person. It's that kind of action that's really going on in the quadrilateral family tree. So once upon a time, there was a quadrilateral, just a 4-sided shape, and it had 2 kids. It had kite and it had a trapezoid. Now, Kite had a kid with who? I don't know, it was a one-night stand. Kite's, kind of like that. Kite had a kid named Rhombus. But here's where it starts to get a little weird. Trapezoid had 2 kids, parallelogram and isosceles trapezoid. And then parallelogram had a kid named Rhombus. So, boy, that must mean that the parents of the rhombus is the kite and the parallelogram. They're kind of like, well, if kite and trapezoid are brother-sister, it's almost like parallelogram had a baby with her uncle, Kite. So you see what I mean? Kind of this family tree's a little weird going on here. And then parallelogram had a kid with isosceles trapezoid, and they called that kid rectangle. Well, that means parallelogram and isosceles trapezoid, well, they were brother and sister because their parent was trapezoid. So again, more kind of weird kind of action going on here. And then rhombus and rectangle come along, and they're brother sister. They have a kid named square. So there's all these connections going on in here. But really it all first starts with, there's 2 main shapes, kites and trapezoids, and eventually these things kind of start coming together. So the next thing I want to talk about is this sum-all relationship. Anytime that we move down in a downward stream in the family tree, we can use the term sum. And what exactly do I mean by that? Well, we could start with quadrilaterals, and we could say that some quadrilaterals are kites, and some quadrilaterals are trapezoids, And some trapezoids are parallelograms. And some trapezoids are isosceles trapezoids. Some isosceles trapezoids are rectangles. Some parallelograms are rectangles. Some parallelograms are rhombuses. Some kites are rhombuses. And some rhombuses are squares. And some rectangles are squares. Now, we could also kind of use the transitive property with this at the same time. We could say that, well, if some kites are rhombuses and some rhombuses are squares, then by the transitive property, some kites through a rhombus, some kites are squares. So you can skip over shapes as long as it's still going down in a downward trickle, that we could connect together two shapes that aren't necessarily right directly downstream from each other. So again, another example would be saying that some trapezoids, and again, as long as I go in a downward direction, some trapezoids are squares. Some trapezoids are rhombuses. So we get that sum relationship here. And again, we can use the transitive property. You know, we can skip over a particular shape. We can skip over rhombus to say that some kites are squares. Some isosceles trapezoids are squares. Some quadrilaterals are rectangles. That works. The all relationship is when we move backwards against the stream. We get to say that all of the one shape we're talking about is the other shape that's upstream from it. So for example, all squares are rectangles. All rectangles are parallelograms. All squares are rhombuses. All rhombuses are parallelograms. All parallelograms are trapezoids. All rectangles are isosceles trapezoids. All isosceles trapezoids are trapezoids. All trapezoids are quadrilaterals. All rhombuses are kites. And all kites are quadrilaterals. And again, we can use the transitive property here. That if all squares are rhombuses and all rhombuses are kites, that means that all squares are kites. It also means that all squares are quadrilaterals. So again, the transitive property works downwards, downstream, and upstream with our sum or our all. Now the last little part I want to talk about is, well, is it true that some kites are parallelograms? And we notice there is no direct downstream relationship. But here's the thing, there is a relationship, and we get to look at, is there a downward trickle from both of these shapes leading to one specific shape? And so kites lead to rhombuses and parallelograms lead to rhombuses. So some kites are parallelograms when kites are rhombuses. So if a kite is a rhombus and if a parallelogram is a rhombus, then a kite could be a parallelogram. So again, there isn't that direct relationship, but if there is a downstream flow into one common shape, then it is true that those two shapes are sometimes the same. They're not always the same, but sometimes the same. So another example would be, is it ever true that some kites are trapezoids? Well, let's see, is there a common shape that both kites and trapezoids flow down into? Well, trapezoids flow down into parallelograms, but kites don't flow into parallelograms. So that's not the sum shape that they have in common. Kites flow into rhombuses, and well, trapezoids flow into parallelograms, which flow into rhombuses. So we could still use rhombus here. Some kites are trapezoids when kites are rhombuses and when trapezoids are rhombuses. So there is that indirect kind of relationship. Okay. Again, another example. Are some parallelograms isosceles trapezoids? That's true when both of those shapes are rectangles. That's true. Are some kites isosceles trapezoids? Well, let's see. Is there a common downward trickle shape? Let's see. There would be, and there's only one here. And that's when kites are squares and isosceles trapezoids can be squares. So some kites may be isosceles trapezoids, specifically when they are squares. Could kites be isosceles trapezoids when they are rectangles? Well, isosceles trapezoids flows downward into a rectangle, but is there any way that we can flow downward from a kite to get to a rectangle? And there's no possible way. The only things that kites trickle down into are rhombuses and squares. We'd have to move up against the current to get to rectangle, or we'd have to flow from a rhombus up to a parallelogram to get down to a rectangle. So is it true that some kites are isosceles trapezoids and they are rectangles? No, that would be a false statement. Again, the only way that kites can be isosceles trapezoids is if and when they're only squares. So we will continue working with our family tree and using these some and all and none type of scenarios to see if statements are true and false. So we'll continue with that later on. A little confusing, I know. Now, what other names, what some AKAs we have for, say, a square? Now, we said all squares are rectangles and all rectangles are parallelograms. So technically squares are parallelograms. Squares are also rhombuses. Squares are also kites. Squares are also isosceles trapezoids. Squares are trapezoids. Squares are quadrilaterals. Holy cow. So a square really is the ultimate incognito shape here. So what other names does a square have? All of them. So you can write all those out if you want, or we could just say any special quadrilateral. We really need to say a square could be called any other special quadrilateral. So a square is a trapezoid, a square is a kite, a square is a parallelogram. Okay, so a square just isn't truly a square. Okay, it doesn't have an exclusive relationship. A square isn't just a square. A square includes, it is inclusive to other names that come above it. What other names does a rectangle have? Well, again, we need to move up, upstream here. So a rectangle is a parallelogram. A rectangle is a trapezoid. A rectangle is an isosceles trapezoid. And a rectangle is just a plain old quadrilateral. But you couldn't necessarily call all rectangles squares or all rectangles rhombuses or all rectangles kites. It just doesn't work that way. We can't go either up and down or down and up to get to it. So what other names does a rectangle have? Parallelogram, isosceles trapezoid, trapezoid, and quadrilateral. Rhombus. What else could we call a rhombus? Well, again, let's go upstream in all directions. We could call a rhombus a kite. We could call a rhombus, well, just a quadrilateral. It's got 4 sides. We could call a rhombus a parallelogram. We could call a rhombus a trapezoid. But that's it. We can't call a rhombus a square always. Now, a rhombus could be a square, but it's not always called a square. A rhombus is sometimes a rectangle when they're both squares. And a rhombus could be an isosceles trapezoid if it's a square again. But we're looking for always. What could you always call a rhombus? We could always call a rhombus technically a kite, a quadrilateral, a parallelogram, and a trapezoid. A parallelogram. Let's move upstream. Now, you'll notice here there's going to start being fewer and fewer things we can call shapes as we move up the family tree. So a parallelogram could be called a parallelogram, but it could also be called a trapezoid or just a quadrilateral. And that's it. There's only really 2 other aliases parallelograms have. Kites. Well, this is going to be easy. The only thing we can really call a kite besides a kite is just a quadrilateral. Now, some kites are rhombuses, but not all kites are rhombuses. So again, we're looking for the all situation here. Trapezoid. Just plain old trapezoid. Well, the only thing we could call it for sure is that all trapezoids can be called quadrilaterals. And isosceles trapezoids. Well, this one we can get 2 names out of. We can call it a quadrilateral, and we can call it a trapezoid. And that's it. Now, again, some trapezoids are rectangles, but not all isosceles trapezoids are rectangles. Now, we're going to look at some statements here, and we're going to try to figure if these statements are true or false, and then we're going to try to explain why these statements are true and false. So I'm going to refer back to the family tree here to kind of help us out along the way. So this says no rhombus is a rectangle. Is it true that there can never be a rhombus that could also be called a rectangle? Well, here's our rhombus. Here's our rectangle. There's no direct link between a rhombus and a rectangle, but is there an indirect link? Like, is there something that links both of those shapes together into one shape that could be called both a rhombus and a rectangle? And there is. A square can be called both a rhombus and a rectangle. So, no rhombus is a rectangle? That's not necessarily true. That's false. What could we say to prove that this really is a false statement? Well, if our rhombus is a square, a square is a rectangle. So kind of using the transitive property there, we can say that a rhombus could be a rectangle. Is it true that all rhombuses are rectangles? No, there is no kind of upstream effect here from rhombus to rectangle. We could go up to parallelogram, but then we'd have to go down to rectangle. But it is true that some rhombuses are rectangles. And again, how do we know if the sum situation, if we can say sum of one shape is the same as another shape? We have to look downstream and see if they meet at a common shape. And rhombuses and rectangles do meet downstream at a common shape when they are squares. All right, the second one over here. Some rectangles are squares. Well, let's see. Here's rectangles, here's squares. When we move down, because we started with rectangles, anytime we moved in a downward direction, let me just remind you and jump back here. If we move in a downward direction, we really do get to say that some of that is true. So is it true that some rectangles are squares? Yeah, it's true that some rectangles are squares. And we could just validate this by saying when the rectangles have, 4 congruent sides, then that rectangle turns into a square. If the rectangle, does a rectangle have to have 4 congruent sides? No, it doesn't. It doesn't have to have 4 congruent sides. So that's why we say some rectangles are squares. Not all rectangles have to have 4 congruent sides, but they could. And then we would call that shape a square. The third one, some rhombuses are rectangles. So are some rhombuses rectangles? And yeah, sometimes rhombuses are rectangles. And when would that happen? When the rhombus is a square and when the rectangle is a square, then that is true. There is that common shape, that there's that downward trickle. So this is kind of related back to the first one here. And then the fourth one, all rhombuses are squares. Are all rhombuses leading down to squares? Now, we're starting here and we're going down to get to squares. So we said going down, we can always say some. Going up, we can say all. Now, this is saying that all, and we're going in the wrong direction. So it's not true that all rhombuses are squares, because if you think about it, to be a rhombus, we had to have 4 congruent sides. And do squares have 4 congruent sides? Absolutely. But squares also have 4 90-degree angles. And do rhombuses have to have 4 90-degree angles? No, they really don't have to have them. But could they have them? Absolutely. Then we would call that rhombus a square. So this is false. Not all rhombuses are squares, because we could say not all rhombuses have right angles, or another way of validating this would be, well, instead of saying all, we should really say some. So you can, 2 different ways of proving that your answer is false in this case. You could say, well, change this word to some and then it's true, or you could just explain how in general this statement is false. So now I want you guys to try, to finish out the video here, try these last 4 statements, and we'll go over these together in class the next day. So good luck.